Hello everyone. So this is a question from NEET 2025. Given below are two statements. One is labeled as assertion and the other is labeled as reason. Assertion is, so we have one, two, three, four carbon atoms. So iodobutane undergoes SN2 reaction faster than again one, two, three, four carbon atoms chlorobutane. Okay. Reason is iodine is a better leaving group because of its large size. So choose the correct answer from the options. So few options are given to us and the chapters involved is haloalkanes and haloarenes. So before we go and see the assertion and reason, some prerequisite about SN2 reactions is important since they have mentioned that. Then also leaving groups are important, right? So let's talk about it. Halogen atom in haloalkanes. Okay, so haloalkanes are, they can be represented as Rx, and the bonding is, there is a bond between C and the halogen X, right? So halogen atom in haloalkanes is more electronegative than this carbon atom attached to it, right? So therefore, obviously being more electronegative, so this guy will pull these electrons more towards itself, right? So therefore, carbon acquires a partial positive charge and halogen atom acquires a partial negative charge. Okay, so let's denote these charges as positive and negative. And obviously we have, three other valencies of carbon. Because of the presence of this small partial positive charge on carbon, nucleophilic reagents, okay, so I have used the term nucleophilic reagents. So nucleophilic reagents are those reagents having negative charge or a lone pair of electron, okay. Those reagents having negative charge or a lone pair of electron. Okay. So again, I will repeat my statement. Due to the presence of the small positive charge on the carbon atom, nucleophilic reagents can attack this carbon. So whenever we have a nucleophile which is stronger than the halide ion, right? So obviously a nucleophilic reagent will generate a nucleophile and this halogen can become a nucleophile halide. So if you have a nucleophile, if it is stronger than the halide ion, whenever it approaches the positively charged carbon atom of an alkyl halide, this is the alkyl halide, halogen atom, so this guy X with its bonding pair of electrons, so it takes these bonding pairs of electrons, it is displaced, so it goes out in the form of X minus, and a new bond between C atom and the incoming nucleophile is formed, right? So it can be also shown using a reaction. So that is, a nucleophile, we have Rx. So what will this guy do? It will attack the R because R contains a partial positive charge, X contains a partial negative charge. So this nucleophile attacks this R and it will form a new bond, make a new bond with this R. This X, the halogen, will take these bonding electrons and become a halide ions. They will leave as halide ion. So therefore, the products will be getting as RNu and X minus. So this is known as your leaving group. So the outgoing nucleophile is known as the leaving group. Okay. Now, better the leaving group, more easier is the nucleophilic substitution reaction. Very important statement. Okay. Better the leaving group, easier is the nucleophilic substitution reaction, and it is true for both of them, SN1 as well as SN2. Okay, SN1 and SN2 are just two different mechanisms. And among the halide ions, the order in which the leaving group departs, so their sequence is I minus, Br minus, Cl minus and F minus. So this is the order, or with the ease with which I minus can go out very easily. Then we have Br minus, then we have Cl minus, then we have F minus. Because of this, iodoalkenes are more reactive than bromoalkenes, then chloroalkenes, then fluoroalkenes towards nucleophilic substitution reaction. Okay, so we will see the reason behind this. Why is this the case? Why is this the order? Okay, before that, let's just spend some time discussing what is SN2 exactly. So there are two types of nucleophilic substitution. This is in general what happens in a nucleophilic substitution. There is two ways in which this reaction can happen. So two types of nucleophilic substitution. So we have SN2 and SN1. Okay, so S stands for substitution, N stands for nucleophilic, 2 stands for bimolecular. Okay, S stands for substitution, N stands for nucleophilic, 1 stands for unimolecular. So SN2, it follows the second order kinetics. That's why we have a 2 here. The 2 is standing for bimolecular. Okay, that means in the rate equation we will have two concentration terms. So whenever you want to write the rate equation for this in case of SN2, so it will be K into the concentration of nucleophile as well as the concentration of the substrate, that is your haloalkene. Both of them will be there. That's why it is bimolecular. Okay, and also no intermediates are formed in SN2, takes place in one step, and also accompanied by inversion of configuration if you have a chiral carbon, if you have a chiral compound. Okay, now coming back to the reason behind this. Okay, so there is a popular misconception, that is people think that greater is the polarity of CX bond, more reactive should be the haloalkene. Okay, this is simply not true. Okay, I will give you an example. For example, in methyl halides, that is CH3X, the order of polarity of the CX bond is CH3. Obviously, the polarity is decided by the dipole moment. Okay, so in the case of CH3Cl, dipole moment is 1.86 debye. Then we have CH3F, the dipole moment is 1.847 debye. In CH3Br, the dipole moment is 1.83 debye, and in CH3I, the dipole moment is 1.636 debye, right? So therefore you can see this is the most polar bond because it has the maximum dipole moment, then CH3F, then CH3Br, then CH3I. So therefore this is the order. So therefore this should be the reactivity order 2. That is not correct. This logic is not correct. Okay, but the actual order of reactivity is Ri, Rbr, RCl, and Rf. This is the actual order of reactivity towards nucleophilic substitution reactions. Okay, that is because reactivity depends upon how easily the CX bond can break. Very important, that reactivity depends upon how easily CX bond can break. Okay, so when we look and see the mechanism, can you see here what is happening? Obviously nucleophile is attacking, but simultaneously this bond is breaking, right? So easier to break this bond, better will be the leaving group, and easier will be the nucleophilic substitution. When we compare in terms of polarity, polarity just tells us how electronegative is this guy, and how much time electron is spending near this guy. That doesn't tell us about the strength of this bond. That's why it's better to compare their bond dissociation enthalpy instead of their polarity. Okay, so therefore this logic, hence it doesn't work because we are looking at their polarity. Hence we should look at the bond dissociation enthalpy of this CX bond. Okay, so bond dissociation enthalpy decides the order of reactivity of the CX bond. Okay, so to support my case, I have some data. For example, the bond dissociation enthalpy in CH3F, the CF bond, is 452 kilojoules per mole. In CH3Cl, the bond dissociation enthalpy is 351. In CH3Br, it is 293, and in CH3I, it is 234. So Ci bond has the minimum bond dissociation enthalpy. Okay, so can you see, as the size of halogen is increasing, fluorine smallest, iodine largest, the bond dissociation enthalpy is decreasing, right? Okay, so this is happening because if you want to compare the Ci bond, so let's say this is the carbon atom, and let's say this is the iodine atom, and let's say we draw CF also. So CF will, the carbon will remain same, but the fluorine will be a bit smaller in size. So can you see, because iodine is larger in size, the overlap is less, so therefore it is easier to break this bond. But in the case of CF, the fluorine atom is small, so the overlap is quite strong, therefore it is tough to break this bond. That's why in CH3I it is easier to break the Ci bond, and hence the bond dissociation enthalpy is the least, right? So therefore Ci will be the easiest to break, and hence if it is easiest to break, it can quickly take these electron pairs and forms I minus or the leaving group easily. Okay, so therefore iodoalkanes, that is RX, are the most reactive. Okay, and this logic applies in both SN1 and SN2, because both are, manifestations of the same reaction. So now we can, go back and check the assertion and reason. So assertion is saying 1, 2, 3, 4, iodobutane undergoes SN2 reaction faster than chlorobutane. Correct, as I told you, because the bond dissociation enthalpy of this bond is less compared to the bond dissociation enthalpy of this Cl, and hence therefore this can easily form I minus compared to Cl minus, right? So therefore this is a correct statement. True. And let's see the reason. Iodine is a better leaving group because of its large size. Yes, because this is, let's say this is carbon, let's say this is iodine. It is difficult to break this bond. Sorry, it is easier to break this bond because of the bigger size of iodine. And then we have C and carbon and chlorine a bit smaller in size. Due to more overlap, it is tougher to break this bond. So it can easily form I minus compared to this Cl minus. So therefore, yes, iodine is a better leaving group because of its large size. Correct. So therefore reason is also correct. True. And it is also the correct explanation of this assertion. So therefore the answer will be C. That is, both assertion and reason are true, and reason is the correct explanation of A. Okay. Thank you.